Um, Welcome to this presentation of MPAI-CAE version 2.2. MPAI-CAE is one of our major standards, and the fact that we are already at version 2.2 indicates that this standard is a longer story. Before going there, let me give you two words about MPAI. So we have MPAI is an international and affiliated non-profit standard developing organization. It develops AI-based data coding standards, and it attaches clear intellectual property rights licensing framework. Two words about this. The goal is to make a standard accessible and timely available. And we achieve this goal by the following steps. Before we initiate the standard, the active principal members develop and adopt a framework license for that particular standard. Framework license is not a license because it does not contain the main elements, values, and other dates and so on. But what is important is that it declares that the rights holder will eventually license their technology at a price that is comparable with similar standard technology and not after products are on the market. During development, any member making a contribution declares it will make its license available according to the framework license. And after the development, MPAI facilitates the creation of a patent pool, and members holding IP in the standard select the preferred patent pool administrator. So this is the service that the additional service that we do compared to other standards organization in trying to make standard accessible and timely available. So this is the MPAI organization. We are working on quite a few matters. Today we were talking about audio, and this will be the task for Marina. But before that, let me give you two words about how we develop standards. We have a very rigorous method to develop standard. We develop use cases and functional requirement. We develop commercial requirement, the framework license I've just talked about, and we should call for technology with attached functional requirement and commercial requirement. Commercial requirement, again, is the framework license. Then we develop standards, but only MPAI members can participate in the development. And the standard essential patent holders select patent pool administrator, as I have just said. MPAI tries to develop a standard for a better AI by making intense use of the technology. So we make explicit the computing workflow of AI applications. So we achieve that by breaking monolithic AI application into a set of interacting components that exchange data with known semantics as far as possible. Then the developers can compete offering components which have improved performance but are standard. And therefore, it's possible for humans to select applications whose internal operation is more or less understood by them. Of course, the more or less is because in AI, you cannot, as it was often possible with previous technology, to know exactly what happens inside. But by breaking up the application, you can achieve a better understanding of the operation of the standard. So this is what we do. Is our standards are component based, subdivided in smaller components, aggregated into one or more AI workflows, and executed in a standard environment. And this is the standard, and this is the framework. But more you will hear because MPAI-CAE makes a big use of this framework. So we also wanted to create a sustainable ecosystem where we have developers, integrators, consumers, and so we have an independent organization called MPAI-Store that guarantees that all components are interoperable, trusted, and available. So this is how the ecosystem works. So we have MPAI developing standards. We have developers developing implementation. We have performance assessor that perform the that assess the performance of an implementation. If this is okay, then it can be submitted to the MPAI-Store. The MPAI-Store assesses the conformity of the implementation to a standard and posted it for end users to download. So this is my last slide, and it gives you quite a long list where you see standards, names. In italic, it means that we are working on them. This is the case, for instance, of 2 video coding standards we are actively working on, and also for online gaming. But we have in total 12 standards that have been approved, and we are very proud of them, particularly because many of these standards have been adopted by IEEE, and our standards have 33 and 2 digits to indicate. For instance, the CAE context-based audio enhancement standard is 3302/2022, but we have a more recent version that is in the process of also being adopted by IEEE. Thank you for your attention, and now I leave you to Marina, who will talk about the MPAI-CAE standard. I think we can close here.
Good morning, good afternoon, good evening, everyone. Today we'll be introducing a brief overview of the work that MPAI-CAE did, but especially introducing the version 2.2, which was recently approved by the General Assembly of MPAI. CAE stands for Context-Based Audio Enhancement, and I am Marina Bosi, the chair of MPAI-CAE, and I'm at CCRMA at Stanford University. So just to really starting from the high up, the basic structure behind any of the work in MPAI is that what we call the MPAI-AIF. And what does that mean? Means that we have a Lego type AI standardization. So we have inputs, outputs, and we have what we call an AI workflow, AIW. And the AIW is composed of multiple AI modules that we call AIMs. So this is kind of the basic footprint for any type of standardization in MPAI. MPAI-CAE technical specification, we call it TS version 1.4, was also standardized by IEEE as 3302-22022. And we have 4 use cases. From now on, we call them USC. The emotion enhanced speech, EES, basically where we're enabling the conversation of individual emotionless speech segments into segments that have a specified emotion. And the audio recording preservation, ARP use case, which is probably one of the most successful, if I may say so, cases within MPAI, where we are creating a preservation copy and access copy out of a digitized open reel magnetic tape for long-term conservation and full correct access and playback. Speech restoration system, SRS, enables the restoration of damaged segments segments of digital vocal tract by replacing it completely, not trying to fix the problem, but just substituting audio based on a neural network that recreates the sentence from scratch, basically. Enhanced audio conference experience, another very successful use case, enables an improved auditory experience. And of course, we started this work in the middle of the pandemic, so this was a particular useful use case. And what EAE does, analyzes and transmits environmental spatial information, separates different sources, specifically speech signals, and reduces the background noise for intelligibility. So version 2 came soon after, and the main new addition was a new composite AI modules, the audio scene description, ASD, which can be viewed as a generalization, if you wish, of the EAE, the Enhanced Audio Conference module. So this is what we call the structure of the composite AIM. Oops, sorry. We have a microphone array geometry, at least in the original version 2.1, a microphone array audio, and we transform the audio from the time domain to the frequency domain. We localize the different sources, spatial attributes, synthesis, and then packaging into an audio scene description. And so this is the composite AIM. Version 2 also started looking into a new web-based organization of the standard specifications. So we have the normative workflow connections, and that specifies the function of the AI workflow and the different AIMs, and normative input and output data with semantics and syntax specified as a normative part of the standard. For example, the data format, if we're looking here, are all connected to the web. So if I'm clicking on that, you see the different type of data format. And if I'm clicking on audio, for example, I have all the information that is pertaining to the audio. The data type is rendered in the audible human range, so in between 16 and 20 kilohertz, 16 hertz and 20 kilohertz, and so on and so forth. So this is all the attributes of, if you wish, of the audio data type. So going back to, can you see my slide? Or, I mean, were you seeing the slide, or were you seeing the connection with the web? Any feedback?
Only the slide.
Apologies. All right, I have to do it in a different way. Okay, so continuing on, the version 2.2 is again an even more refined method to publish MPAI technical specifications. It doesn't apply only to CAE, but it applies throughout the MPAI standards. And basically, it consists of a series of web pages, and each page basically covers a chapter of the standards, and it's organized in a hierarchical way. For example, in one page, we have the AI workflows, and each workflows then links to the AI modules relative to that workflow and the data types that are used in input and output of the workflow. Then once we focus on the AI module, we have one page for each AI module, which include links to data types that are used in the AIMs, And if the AIM is a composite AIM, it also links to the different AI modules that are the core of the composite AIM. Again, this is not just something specific to CAE, but it's across the board for the MPAI standards. And so we can see kind of a cross-pollination in between the different type of standards. For example, the television and media analysis AI workflow references AI modules, AIMs that are derived from CAE, and other MPAI standards. So each version, each technical specification, I should say, has its own page or its own set of web pages, all connected hierarchically. So let's see if I can, actually try to do, so let me share this, if this works. So this is an example of a case of CAE, because we are presenting CAE, of the CAE's use cases version 2.2. So essentially, there are not conceptual differences in between version 2.1 and 2.2, except the organization, which is web-based and interactive web-based. And so the use cases are defined as I described, but the way the standard is published is completely different. So we have a foreword, an introduction, scope, definitions, and I, for example, talked about the AI workflows. Can you still see the, yeah, excellent. So you see the 4 use cases I was referring to: emotion enhanced speech, audio recording preservation, speech restoration system, enhanced audio conference experience. And so, for example, if I look at the audio recording preservation here, I have the different functions, the reference model. So here we have the reference model that shows the workflows for this ARP use case with input, preservation audio files, preservation of the video files, and output access copy files and preservation master files. And as we can see here, we have 5 different AIMs, and we have the IO data for the workflow, but then here we start looking at the AIM specifically. If I click, for example, the audio analysis AIM, this is still version 2.1. We have inputs and outputs of the audio analysis for preservation. And we have the input data, the output data, and we have no sub AIMs because this is not a composite AIM. But then we can look at the JSON file relative to the MPAI-CAE ARP audio analysis for preservation AIM, and so on and so forth. So we have the description file here. So, but let's maybe quickly take a look at the ASD composite AIM. See if I can. If I can get there. So as I said, ASD is a composite AIM, and here we are. So again, this is the function description, the reference architecture. So you have the input and output, but now we have sub AIMs in this particular case because this is the composite AIM. So we have multiple AIMs that are described in this composite AIM. And again, these are the AIMs that we can always access. For example, the audio analysis transform has the same type of structure. that we saw before. And again, we can go to the JSON. Oops. Maybe not. For example, if you go to the JSON metadata for the composite area, we have the description, this is version 2.2 and so on and so forth. So this is kind of in a nutshell, the structure of version 2.2. If you are familiar already with version 2.1, you probably see all the technical characteristics. What's new again is the web organization. And so sorry, trying to. Right, I would like to close thanking the Leonardo. I think this is really 2.2 is really his brainchild. So thank you, Leonardo, for providing us with that. And all the members of the MPAI-CAE for their invaluable contributions, including Sergio Canazza from University of Padova, Mert Koteli from METU, Hussein from METU, Mark, and many others that contributed to the work. So this is concluding my presentations, and we can open it for questions if you have any questions. I guess, yeah. So please join MPAI if you're not already a member, and thank you for your participation.
Close here.
Hello, everyone, and thank you for the opportunity to present this proposal today. Thanks to Leonardo and Marina for inviting me to give a brief presentation reviewing a proposal that I'm making to MPAI-CAE. So you see on this slide that I just basically I'm submitting this new proposal, and I'm going to go over it pretty quickly, including some audio demonstrations, which will be, if you have headphones, that'll be ideal as a way to experience the demonstrations. We'll verify that you're hearing stereo, which would mean that you would, if you're using wireless Bluetooth headphones, then select another microphone than the microphone of your Bluetooth device to make sure that you're going to hear stereo. But if you cannot use headphones, it should be fine. A quick summary of my own background, because this proposal is sort of a culmination of a number of experiences that I've gone through over the past few decades, starting with EarCam, which I'm going to describe the SPAT software as part of this proposal, and with various stages, including game audio and broadcast, as well as augmented and virtual reality. So this proposal sort of combines these various experiences. And more recently, over the past 2 years or so, I have run a consultancy called Virtual Works, which has crystallized a few of the concepts, including one I'm presenting today. So as a general outline, I'm going to talk, there are two main parts in my proposal, but the one I'm going to highlight is called reverberant spatial audio objects, which is something that my understanding is that it ties to some of the objectives of MPAI and specifically CAE, but more generally speaking, other also scene description and object-based audio, things that I see in other parts of the activity. The relevance in terms of time synchronization with the activity of MPAI is less clear to me, but certainly my understanding is that this proposal could fit well in as a response to the current call for technologies issued by CAE, six degree of freedom specifically. In terms of the state of the art, what we have to the situation today for 6 degree of freedom audio is that we can say that for game audio, video game, and virtual reality, it's a de facto assumption that the audio is 6 degree of freedom and navigable by the virtual listener or the end user. But when we're distributing linear audio, such as recording, music recordings, movies, etc., or podcasts, typically it's the interactivity is limited because it's linear recorded audio. One would expect the interactivity to be limited, as well as the presentation is not 6 degree of freedom. In other words, it's not possible to experience the scene from various point of views, including translation. So the consumer of the recording can only rotate in with 3 degree of freedom. This proposal is attempting to address this fragmentation by allowing if the content creator wants it, even in the case of a recording, to allow navigation and 6 degree of freedom interaction for the end user. And in the case of virtual reality or teleconferencing experiences, to enable those to be, these experiences to be distributed to any device that is compliant to a certain approach that I'm proposing here for the way that the device will understand the scene it would render and render it faithfully. So this is a quick summary of what the thrust of my proposal here. And so in terms of, I've already pretty much summarized the current state of consumer spatial audio technology. So I'm going to skip this slide. And I'm going to start with a quick demonstration that illustrates in the context of a virtual or augmented reality experience how audio and video work together. And this, I'm going to comment a little bit more about how this was done. It's a few years ago, a demonstration of the technology that my team was developing at Magic Leap. So if I click here, you should hear, yes. Okay, so just saving a few minutes by getting out of. Okay, so a few comments on what you just heard. Hopefully you were able to, for those of you who were wearing headphones, you heard spatial presentation. Okay, and I'm just going to comment briefly on what you'd heard. So first of all, there were both video and audio, and the two presentations were synchronized. And an object was in your field of view, the intent was that the sound would appear to come from where you see the object. This presentation was captured from what would have been seen by the person wearing a head-mounted augmented reality device made by Magic Leap at the time. That was the first generation of the Magic Leap device. So it's already looking more bulky than the current generation. And what's useful also to mention is the distinction between the application, which is the generation of the content, and the rendering engine. So the rendering engine in this case is running on the device, and it's just executing instructions that are coming from an application. The application is a specific one that the creator of the application wanted to share. In this case, it's a musically influenced game where the end user can actually create the music and place it in space. So you heard some loops that were actually supposed to be created by the person who is playing the application. So an application was developed by created by the developer that was then distributed using the Magic Leap infrastructure as a Magic Leap application, and the end user is able to interact as if it were a video game with the content, which in this case it's musical content. And with this, we can imagine things that would be possible in the future. For instance, this could have been a live music, or you can, by extension, it could have been a sport event or a virtual meeting where we have both a video and an audio presentation. And in the future, it would be useful, potentially exciting, if when we experience a sport event, every element of the scene that we can see also had an audio counterpart that appears to come, as in the real world, from the same direction, from the same place. And when we rotate our head, the presentation, both video and audio, gets updated accordingly. And if we translate, if we navigate in the scene, that happens. Another possibility would be that if you create a musical recording, in some cases, it would be the creator may be interested in allowing the consumer of the recording to interact with the content, like maybe remix it or replace some of the instruments. Today, this is not possible with the current distribution formats that are available to us for spatial audio distribution, such as Dolby Atmos, for instance. And another possibility would be if you imagine a movie soundtrack that you would like to be able to distribute internationally. There is now possible, thanks to artificial intelligence and machine learning technologies, to replace the dialogue, any particular, the voice of any particular character by one that's speaking a different language, and have even their lips updated to reflect that they're speaking a different language. With today's modes of recording, that it would be very difficult to share this, to distribute this kind of experience. So these are just some illustrations of what we could imagine as future 6 degrees of freedom or user interaction and content creation experiences. One example would be a live music experience in a concert hall where some of the attendees or some of the participants of the experience are wearing an augmented reality device, and some of the objects that are presented to the consumer are virtual. They may not be there. Even if you're in the venue yourself, maybe the lead singer is actually a remote person who's virtually joining the experience, as if it were, for instance, a video, similar to a video conferencing experience. What's often assumed if we create or distribute this kind of experience is that the system that plays it, like the device, would have to be aware of the geometry of the venue in order to properly render convincingly the audio experience. This actually is restrictive, and it's actually not necessary. So what we can now accept as an approach to audio experiences is that it's not a requirement to authentically simulate the venue or the scene that is being presented, more than just obtaining plausibility. In other words, obtaining creating for the end user the experience that this could be true. This could be a scene that exists, but it doesn't have to be faithfully reproducing reality. And what that means is that we have an opportunity, we have extra flexibility to introduce aesthetic choices in creation of these kinds of experiences and artistic decisions on the part of the creator that could be assumed to not be possible. And this is going to be core to this proposal. So we're actually going to make a distinction between authentic simulation, plausible simulation, and finally introduce in the few minutes I have considerations of making the solution commercially and practically viable. So this raises questions of interoperability of devices and applications that I want to address in this proposal in the few minutes that are left. So one thing we are going to need, and I'm going to be skipping very briefly on this slide, is that we need to be able to have, we want a wide range of devices to support the rendering model, and that means having a very computationally very efficient rendering model, which we are going to have the opportunity because not aiming for perfect authenticity means that we can optimize the rendering engine to make it more scalable and more adaptable to a wide range of devices, including battery-powered mobile devices. So part of this proposal leverages recent progress on rendering many 3D audio objects in a very cost-efficient manner, meaning that for any additional object we want to render, the incremental cost is very low. There's been also, so this is actually a slightly broader representation of the engine that was running in the Magic Leap demonstration that I showed earlier. So we have very mature at this point, several decades of progress on optimizing spatial audio rendering engine and making them agnostic to the playback configuration, knowing that headphone playback is actually one of the most challenging modes of reproduction. We have also made progress into specifying audio rendering engines that support navigation between multiple rooms through an underlying architecture that is actually very compatible with the way that digital audio workstations work to operate today. We also have the ability to simulate an existing room in a very convincing way, in such a way that when if you're in a situation with an augmented reality device where you're hearing real sounds in the room where you are, but where the experience includes overlaying sounds that are virtual, maybe the sound of a virtual character or a virtual participant in a conference. It's now possible, we know how to make the experience so plausible that with your eyes closed, you wouldn't be able to tell which of the audio objects that you're hearing as a consumer are really in the room with you or are remote. So that is also a part of the solution that is well understood today. So being able to render efficiently and in a scalable way the content is essential. Another element of this proposal is enabling the author to transmit their intention in a flexible way, even if they are primarily focused, motivated by perceptual and aesthetic goals, not only simulating the physics of an existing environment or an environment that's being built. And finally, I mentioned addressing issues of interoperability of applications and devices. So basically, for a given application, it can be rendered on a wide range of devices, whether they're earbuds, headphones, soundbars, home systems, or cars. So any application can be compatible with a standardized rendering model that is implemented in in a wide range of devices. But conversely, any device is compatible with a wide range of applications. So it's no longer necessary for, say, a Magic Leap device to only be compatible with Magic Leap authored applications. But on the contrary, supporting a wide range of unconstrained applications through an underlying description of the scene that is standardized. So I have only 3 minutes left. This is an example of a purely aesthetically motivated user interface. This is a quick representation of an object-based audio, a piece of object-based audio content. This is also very mature technology today, but limited to not to dry objects. The way that for linear audio content, the way it can be distributed is fundamentally limited to 3 degrees of freedom and limited interaction. So this proposal addresses these issues by partitioning or defining a low-level rendering model that can be a standard, that it can be adopted by any device, as I mentioned, but is also known by the creators of applications in such a way that any application can also come with a scene description interface that allows it to speak in the language that all devices speak, and is not limited in terms of only being dry objects, so basically fundamentally 6 degrees of freedom reverberant audio objects, and in such a way that if the creator wants it, the creator can enable the end user to interact with the content, such as navigating. And in the last 2 minutes, I'm going to demonstrate this with SPAT. So SPAT is a software that I developed. It was actually, this model was part of the MPEG-4 perceptual approach when it was standardized back in the early 2000s. And what was not addressed by that standard is separating the high level and the low level and trying to standardize the low level rendering engine. So that's essentially what we're doing here. So we're able to leverage what we've learned through that experience, but in such a way that we also address interoperability that was not addressed in this previous standard. So in the 1 minute left, I'm going to go to, let me quickly show. Yes. So a quick comment is that the underlying audio rendering engine is compatible with what I described earlier. So the Magic Leap device could actually play the content I'm going to play. And the rendering engine can auto-configure itself so that when it receives an object, it just automatically just executes the instructions that it's asked to execute in order to render this object dynamically. Okay, so also before I finish with this demonstration, I'm going to illustrate the fact that the end user can interact with the content at various levels. That's part of the proposal as well. I'm going to illustrate them quickly with a demonstration. So there are various profiles of interaction that the creator of the content can authorize on the part of the user. Okay, so that's all I'm going to have time to present. So I'm going simply, this was the last slide. So I'm going to finish only with the demonstration, but this slide deck will be available anyway for you to consult after this presentation. So I'm going to do I still have, like, maybe, oh, it's already 10:01. So do I still have,
We can use a couple of minutes, please,
okay,
that's
thank you.
fine.
Thank you so much. So let me start Max. You should be seeing Max right now. I'm going to turn this on. We're going to play. So what we see is the user interface of the SPAT software. So in this case, we're going to show what the creator could do, which is that they have three instruments. They're creating a spatial immersive audio mix. And I'm going to first demonstrate something the creator might do while they're creating this content. So let's see if you hear this. I'm going to mute. This should be only the left ear, and this should be only the right ear. So hopefully if you're wearing headphones, you hear, I'm taking object one and I'm moving it around. I'm going to leave it at this spot, play the second object. So as you can see, as the content creator, I can place the objects in a place I like. Of course, the tracks were done in previously. And I'm introducing a third object. Okay, so now we have three objects that as a content creator, I can move them in space and provide a description of this content to a consumer. If, as the content creator, I want to allow the consumer to interact, oops, sorry, let's stop. If, as the content creator, I want to allow the end user to interact with the content, it's possible with this proposal for the end user to have an application, which in this case could look the same as this, where the objects appear on the UI that is presented to the consumer, and then the consumer can do the same thing, which is, in this case, it's a coincidence that we are showing the same application for the creation of the content and the end user interaction. But what could then happen is that the end user has the content and, for instance, remixes, changes the position of certain objects, maybe even, since this is 6 degrees of freedom, rotate some of them. So I'm going to take the first source and I'm actually going to stop everything and play only one source. So this is object number one, and I can simulate rotation of the object. You see that on the UI, the object has some directivity and it's able to turn on itself. And the end user, just to stop that, the end user could also navigate in the scene, although that's not demonstrated here. But if it's possible to change to control the orientation under which the end user sees an object, then it's possible also for the user to rotate, to basically move in translation and go behind the object if they want to. It's not a feature of this this demonstration. And then to close, what I can show is that I was mentioning that headphone spatial audio playback is a challenging thing. And in this case, I'm using a technology called Externalizer developed by VirtualWorks also, which attempts to address this limitation. I'm just going to quickly demonstrate that. So I'm going to play that object number one, and remove this Externalizer technology just so to illustrate one particular challenge of headphone audio playback, which maybe for you who are using headphones, you'll be able to appreciate the difference. So in this case, we have one sound, and for me, it turns out that we're using my head relay transfer function. So I'm able to hear this sound moving in front of me. But if I turn off this externalizer enhancement, now the sound is elevated. So I no longer have a frontal scene. I'm no longer enjoying a frontal presentation. This is just for somebody who would know that headphone rendering technology has limitations in terms of how convincingly it can reproduce audio object, spatial audio object, especially in the front. This proposal can include an extension of the rendering technology that attempts, I believe, remedies that problem as well. And that's going to conclude my presentation. Thank you so much.
Excellent.